This video is on intramolecular and intermolecular forces of attraction. Mostly what we're going to be talking about is intermolecular forces, but the first line here you can see a covalent bond, a bond where two nonmetals share electrons, is the result of intramolecular forces. So that's with an A. Intermolecular forces are attractions between two different or more than two different molecules in liquid and solid states. These are much weaker than covalent bonds. So covalent bonds are stronger than those. This helps you determine physical properties of a compound, such as your boiling point, your melting point, and your solubility. There are three types of intermolecular forces that we are going to talk about. These intermolecular forces form between a partial charge on one molecule and the opposite partial charge on another molecule. So remember our partial charges, we had a delta positive and we had a delta negative charge. We know that opposite charges attract, so this positive and this negative are going to be drawn towards each other. Polar molecules, recall how we can determine if a molecule is polar or nonpolar. A polar molecule have permanent dipoles, where nonpolar molecules can form temporary dipoles. Remember, a dipole looks like this, with your arrow pointed towards the more electronegative element. So here are the three different types of intermolecular forces that we will talk about. We have the first type, which is called London dispersion forces, or just dispersion forces. You'll see me abbreviate that LDF. The second type, we have dipole-dipole forces. And the third type, we have something called hydrogen bonding. These are in order from the weakest type of force to the strongest. So hydrogen bonding is our strongest force. LDFs are our weakest force. And then dipole-dipole is right in the middle between the two. London dispersion forces are the easiest to identify because all compounds and elements have them. No matter what you are working with, they all have London forces. So how do these dispersion forces work? So if you're looking at a nonpolar compound, the electrons in them may shift. So we know electrons are constantly moving. When we drew our Lewis structures, if you recall, if we do the dot structure for carbon, we said carbon has 4 valence electrons, so we placed 4 dots around it. But in reality, these electrons are moving in the electron cloud. They're not just stagnant, top, bottom, left, and right. They're moving. So this movement causes these temporary dipoles, these pluses and minuses to form and then go away. So what these temporary dipoles do is that they induce or form another temporary dipole in a nearby molecule. And then the delta positive on the one molecule is attracted to the delta negative on the other molecule. Again, this is the weakest of the attractions, LDFs. Every molecule has these. You do not have to think about it. So letter A here to the left, if you have an even distribution of electrons, you can see it's all separate. There are no dipoles. There's no pluses or minuses. This would be like a nonpolar molecule. If you have a temporary dipole, notice how you have your positive and your negative here. And when you get that temporary molecule, that temporary dipole, that causes the neighboring molecules to have their own dipoles. And that's what you see in part C here. And that's when all of the molecules have those plus and minuses. They will not last forever. Now, if you're comparing two molecules and the two molecules only have LDF forces, let's pretend they don't have dipole-dipole forces or hydrogen bonding. The larger molecule have stronger dispersion forces. And by larger and smaller molecules, we just mean by looking at their molar mass. So propane, for example, C3H8, if you added up the molar masses of C3H8, C is 12.01, so that's about 36. H is 1.01. That is about 8. So we're left with 44 grams per mole there, or atomic mass units, whatever you want to look at. And then methane is about 16. So propane has stronger LDFs than methane. And likewise, elements with your larger atoms also have stronger dispersion forces. So your iodine here is larger than fluorine. And when we talk about the size of an atom, we're talking about something called atomic radius. The trend for atomic radius on the periodic table, down a group and to the left in a period, atomic radius increases. So it increases down and to the left. The exact opposite of electronegativity, if you recall, that was to the right and to the top it increased. So this is the exact opposite trend. The next intermolecular force is called a dipole-dipole force. And you have to have oppositely charged ends of polar molecules here. So very important that this is only in polar molecules. So we will have to use our knowledge of polarity and determine if the molecule is polar or nonpolar. If it is nonpolar, we do not use dipole-dipole forces. It doesn't happen. So that's the first step in determining this. See if it's polar or nonpolar. These form between permanent dipoles. So it's not the temporary that we saw with LDFs. This is a permanent dipole. And again, this is our middle intermolecular force. This is stronger than our LDFs, but weaker than our hydrogen bonding. And lastly, we have our hydrogen bonding. The key here is that this is when hydrogen bonds with a nearby molecule, but it only counts as hydrogen bonding if it's bonded to an F, an O, or an N. Any other element bonded to H does not count as hydrogen bonding. And this is taking H's partial positive and it's bonding to F's partial negative, or O's partial negative, or N's partial negative. That's what's happening on a nearby molecule. This is the strongest force. So to show something having hydrogen bonding, you use a dotted line like you can see below. Notice how the F from this molecule is bonded to the H of that molecule. That is hydrogen bonding. Important to note that this bond here is not hydrogen bonding. That is a common misconception. Hydrogen bonding occurs on two different molecules when they come together. The bonding within itself, within this molecule, that is not hydrogen bonding. It has to be a neighboring molecule. Here's an example in water. What happens here? Notice your H from one water molecule bonds with the O in the other. Again, there's your dotted line for hydrogen bonds. If you have hydrogen bonding, you have dipole-dipole forces. So that's kind of like a cheat sheet. That's kind of a shortcut to determine if you have hydrogen bonding, you have dipole-dipole forces. So you would not even have to check for polarity within a molecule if you have hydrogen bonding. I would check hydrogen bonding first. Everything has LDF, so you don't have to think about that. Hydrogen bonding, very easy. Just look for an O, F, or N bonded to an H. If you don't have hydrogen bonding, then you have to work a little bit and see if the molecule is polar or nonpolar. So why do we care about intermolecular forces, in particular hydrogen bonding? This is involved in our everyday lives with the things we eat, our proteins, our energy sources, or our carbohydrates, and then what we're made of, our DNA and our RNA. I really like this flow chart to help determine what type of force we have. Again, me personally, I would look for hydrogen bonding first, because if it has that, it has everything. But let's just look at this. The first question this is asking is, are polar molecules present? If the molecule is nonpolar, the only force you have are LDFs. If the molecule is polar, then you have to ask yourself the next question, do you have any hydrogen bonding? And involved here, we should have H to F as well. It's F, O, and N. If you don't have hydrogen bonding, then it's dipole-dipole and LDF. If you do have hydrogen bonding, then it's hydrogen bonding, dipole-dipole, and LDF. So let's look at this one here. It says, what type of intermolecular force of attraction is present in each compound? Indicate the molecule with stronger forces of attraction. So if I am looking at A here, let's concentrate on this guy first. I'm looking for hydrogen bonding. I do not see any. I don't see H's bonded to F, O's, or N's. I'm looking for polarity. This molecule, notice, is symmetrical everywhere. Symmetry equals nonpolar. So this molecule is nonpolar, which means it does not have dipole-dipole. So the only intermolecular forces this guy has are LDFs. The next guy over here that I will square in blue, again, I'm going to look for hydrogen bonding. I do not see any. I'm looking for polarity. This is not symmetrical. Remember in the other video we talked about all of these would have to be the same for it to cancel. That O makes it not symmetrical. So this is a polar molecule, which means it has dipole-dipole forces. And then of course everything has LDF, so we can put that down. Which has the stronger force of attraction out of the two? We know that dipole-dipole is stronger than just LDF. The next one, HCl or HF. So if we're doing HCl, it helps to draw the Lewis structure so you can see the bonding. That does not have hydrogen bonding. Again, hydrogen bonding, we are looking for F, O, or N. It is polar because there is not the same dipole throughout, right? Cl and H have different electronegativities. So this is polar, which means it has dipole forces, and of course it has LDF forces. And then HF, if we draw that, HF has hydrogen bonding. There's the H bonded to the F. So this has all of them, and we know hydrogen bonding is the strongest, so HF is the strongest. If we are looking at C, we have F2. That would be a nonpolar molecule because it is diatomic. So if it's nonpolar, it does not have dipole-dipole. This just has LDF. And HF, like we just did before, we know that has all of them. So this guy has stronger intermolecular forces. And letter D here, CH2Cl2. We have two H's. We have two Cl's. That looks like a tetrahedral geometry here. Is that polar? That is polar because the guys on the outside here are not the same. So that has dipole forces. It does not have hydrogen bonding. And then CCl4, 6 dots on all the C's. CLs, I mean. There is symmetry there, which means it's nonpolar. This just has LDF. So the stronger one would be our CH2Cl2. The next part here, it says provide an illustration of two NH3 molecules with one hydrogen bond. label the partial charges. So if we're looking at hydrogen bonding, a couple things to remember. That's H to F, H to O, or H to N. Hydrogen bonded is drawn with a dotted line to the neighboring molecule. And then for our partial charges, we're thinking delta positive, delta negative, and the negative would go on the more electronegative atom. So it'd be a good time to pause the video and try this on your own, and I will show you the answer on the next slide. So here are our two NH3 molecules. Notice how your delta positives are on your H's, and it looks like it got cut off here, but your delta negative is on the N. N is more electronegative than H. Okay, you did not learn about these yet, hashes and wedges. That's just showing in the tetrahedral electron geometry how it's positioned, one in front and one behind the bond. We'll get to that later. Important is your dotted line for your hydrogen bonding. And notice your hydrogen bond is between your H and your N there. And then likewise on this molecule, you still have your delta negatives and delta positives.